Hello, everyone, and Happy New Year, if one can still say that on January 10th. My name is Valerie Briggs. I am the Communications Director here at RESNET, and we are so pleased to have you with us today for today's webinar on RESNET Draft PDS 01 Addendum 82 DX AC HP Modeling with RESNET Energy Modeling Director Neil Cruz. Today's webinar, as we do typically, will be recorded, and the audio file and slide deck will be made available after the webinar. If you have questions, hold on to them. Please type them into the question section, and we will try to answer as many as possible in the time allotted. With that, Neil, I'll pass on to you.
All right, thanks, Valerie. I appreciate it. Yeah, so this presentation, I'm actually going to be doing something very similar at the conference here in January, later this month, actually. And so I decided to give the slide template a try out here and maybe promote the conference if you're still considering attending. It's going to be in Tempe, Arizona. So with that, I'll jump right into things here. So mostly I'm going to be talking about heat pumps. We all know that heat pumps are getting a lot of attention as they're seen as a key technology to solve the global climate and energy crisis. We're going to continue to see big pushes for heat pump deployment. And heat pumps are also a sophisticated technology that's still maturing. And we still have a lot to learn about how they work. And for these reasons, RESNET standards have been relatively quiet about how to model heat pumps. There's just not a whole lot of information out there on how they actually perform. And so this MNHERS Addendum 82 is going to aim to standardize the best modeling practices and assumptions for heat pumps and air conditioners. For this discussion and for the addendum itself, I want to start just kind of setting the stage for this. So the scope of this addendum covers anything that's covered by the AHRI 210-240 standard. So that's any air conditioner or heat pump that's rated with a SEER2 and HSPF2 value. Anything else is not covered in this addendum, but we do hope to cover more technologies in future addenda. So just some examples of systems that are not included, that's multi-splits, window air conditioning, portable air conditioning, package terminal air conditioning, package terminal heat pumps, and ground source heat pumps. So let's start just by going over how the systems that we are covering are currently described in the RESNET 301 standard. So in the 2022 version of the standard, I'm just going to start with the minimum rated features. These are the features that raters have to collect for the equipment. And for these air source heat pumps and air conditioners, it's really just the capacity and the seasonal efficiency. And this is actually kind of dated because they haven't been updated to the HSPF2 and SEER2 values. This is as much data as raters collect, and it's really not enough data to give a full picture of performance. The other piece that the standard covers is there's just one paragraph that kind of covers how to model heat pumps. And it really doesn't even say how to model them. It just says what to model and kind of leaves a lot of other things blank. This is from the 301-2025 preliminary draft that has gone out for public review already. And so you can see the markup here. And I'm going to kind of just step through this so people understand. So that draft is removing this piece, which discusses detailed hourly HVAC simulations. And this was removed because that's now a requirement now that all the software tools have to be hourly and provide that detailed simulation for HVAC equipment. So that's been removed. The next section here is that the manufacturer's equipment performance ratings shall be modified to represent the performance of the compressor and evaporator components alone, which means that it doesn't include the indoor fan. And so we have a little footnote here that says there's approaches, it's informative. There are approaches described in these various articles that are referenced in the standard, but it doesn't say how to do that. And I'm going to take a little bit more time to get into what that actually means. So, and I'm going to use this terminology throughout. So we have something called net performance and gross performance. Net performance covers both the coil and obviously the compressor and everything that's attached to it, and the indoor fan, whereas gross performance is just covering the indoor coil and the coil and the system outside, so not the fan. And so as a result, the fan for the net performance adds power and adds heat to the airstream, which isn't accounted for in gross. And the reason why we need these separated is because they need to be modeled separately. The fan may be in a ducting system that is very different from the way it was rated, and so we need to be able to separate that out. The next bit here is the energy uses of all components. The compressor, distribution fan, crankcase heater, they all need to be added together to give the total energy uses for heating and cooling. I think that's pretty straightforward. There's nothing controversial about that. The last sentence that was also added in this preliminary draft is that the COP of the heat pump and air conditioner shall be adjusted for outdoor temperature and part load performance throughout the simulation. And this was added primarily because we discovered that some people were using constant COPs for their simulations, and that's really not reflective of how the equipment actually works. And this was added mostly in response to that, and it doesn't say how to do this, how to make these adjustments. So that this statement is really left up to the interpretation of the software developer to decide how to do that. What's good is most of the software developers, maybe all now, are referencing at least the same document, and then this is kind of informally referencing it because it's not required by the standard. There's a document, we kind of refer to this as the Cutler curves because it was written by someone named Dylan Cutler, who co-authored this report with me back when I worked at NREL. And these curves are generated based on manufacturer expanded performance tables that were collected for a variety of units and then kind of synthesized into sets and normalized curves that we felt were representative of units, the most representative we could find. And so these are used, and this kind of tells how you change the capacity, but there's also curves for energy efficiency ratios and which is related to the COP. So you can use these curves to make those changes. But again, this isn't normative in the standard. It's just an informative note that you can use this approach. So this paragraph that is in the standards right now says a lot about what to do, but not much about how to do it. And as a result, there's a wide range of interpretation, and any consistency that there is across software tools is either kind of informal, as I mentioned, all referenced in the same document, or just kind of coincidental. And so to resolve this, we wanted to make a lot more of this normative standard language that this is how you should go about modeling heat pumps and air conditioners. So we established a working group to develop the standard language to codify most of these best practices. In this working group, it's a working group of the Software Consistency Committee that I chair, and it aims to basically do the best job we can with the information we have available. This working group is made up of the software providers, EnergyGauge and Ecotrope, representatives from collaboration organizations like the Northeast Energy Efficiency Partnerships and the Northwest Energy Efficiency Alliance. We had a few manufacturers engaged, and then people from the national labs. And maybe most importantly, we had people representing ratings, codes, and incentive programs. So obviously RESNET, but we also had representatives from the California Energy Commission. We had consultants that were working with the California Public Utility Commission and consultants that were working with NYSERDA in New York State. All of these groups had been trying to tackle this question of how do we model heat pumps, and so we brought them all into the same group to kind of come up with a solution. So this brings us then to MNHR's Addendum 82, which is the result of this working group and is currently out for public review. My hope is to get feedback on this addendum, and mostly from manufacturers, because this addendum basically explains the assumptions that we need to make in order to represent the full performance of their equipment, given the sparse amount of data that we have available. Now, I'll also say that the software providers have also been reviewing this addendum and starting to implement it. And so we've already been getting comments back through my software consistency committee, and there have been some changes suggested relative to what's currently out for public review. And where that is the case, I'll point it out here. Okay, so let's start with how are the minimum rated features changing? So we started with, if you remember, just the capacity and efficiency, but it didn't specify which capacity and which efficiency, although it said it's here too. It didn't say anything about it. It included COPs, but it was fairly vague about, what additional efficiency information needs to be included. So here we're going to be more explicit. We're going to require data that's available in the AHRI certified directory or on the certificate. And this is the things with asterisks here are things that in addition to what had been required previously. And the reason why we want to reference the AHRI certified directory is that the data is available for all the relevant products within the scope of this this addendum, and it's independently certified. The data is. In addition, we're adding more minimum rated features that can't be found in the AHRI directory, but should be able to be found through product literature or in some cases just visual inspection. So one of those is the number of speeds or stages, and AHRI has kind of three categories of equipment. It's either a single stage, two stage, or a variable speed equipment. Even though they have this categorization and that changes how the equipment is rated, that information is not actually part of the AHRI directory. You can't look at it and find it. Maybe that's going to change in the future. Hopefully it does. It'd be nice if it was easier to find, but usually you can find it in product literature, what type of staging strategy the equipment is using. We also need to know the fan motor type because this informs the assumptions about how much energy the fan uses. And the basic options are either a brushless permanent magnet or a permanent split capacitor motors. Type of supplemental heating. So for the most heat pump equipment, this is electric resistance, but there's also dual fuel, so it can be gas equipment or like a backup furnace. And then in some cases, you can actually have these systems without supplemental heating, in which case there's still a requirement that for at least modeling, you need to have a supplemental heater in case it's needed to meet the load. Because if you're not meeting the load, you're not using energy, and you're basically getting a free credit for not meeting your set points. So the standards require some kind of backup heating. We have the minimum compressor operating temperature, and this is something it's usually found in the product literature. It's usually somewhere for single and two stage equipment where we assume that if you can't find it in the literature, there's a default of 0 degrees, and for variable speed equipment, which is targeting more cold climate applications, we use a -20 minimum compressor temperature. One of the things that came up in comments already is for dual fuel heat pumps, this should be a lot higher. So we're going to propose something around 25 degrees for dual fuel heat pumps, and that's where the compressor shuts off, and any temperature below that, the furnace will kick in. The last one here is the maximum compressor operating temperature. Not all air conditioners are rated or capable of operating in some of the extreme temperatures that you find in the US. And so we included this originally, but I think we're going to remove it because really if you're not selecting an air conditioner with enough that can operate in the conditions you're designing it for, that's a bigger issue than just a HERS rating. So if you're a rater, then this, between these two lists, covers most of the work, most of the changes related to your work in this addendum. Once you've collected this information, you input it into software. The software should take care of the rest from there. So the rest of this webinar, I'm going to go over the calculations that the software needs to perform in order to provide the best estimate of equipment performance for the HERS rating. And I'll also go into a bit more of the rationale behind some of the calculations, since those aren't explained as thoroughly in the normative standard itself or in the addendum. And as I go through this, it's hard for me to kind of keep track of everything sometimes. So I'm going to start by setting up some terminology before we dive in. There are two primary metrics that we look at when we talk about performance: is the capacity of the equipment and the power. And obviously you can get at power from either using the energy input ratio, which is the power divided by the capacity, or a COP, which is the capacity divided by the power. And so we'll sometimes rely on those two to help fill in the performance at various conditions. The other piece of terminology is compressor speeds. So we use minimum, full, and maximum. So what most people think of and what most of the ratings are provided at, the HRI ratings, are at full capacity. Single stage systems obviously only have one speed, so that's what we call full. Two stage systems, we use minimum and full, and for variable speed systems, we use minimum, full, and maximum. And I think a lot of people aren't familiar with this, but for variable speed systems, the manufacturer can more or less select which speed that they want to use for their full load rating. And it doesn't have to be the maximum. It often is, but it doesn't have to be. And so the reason, and there are various reasons why you might want to go one way or the other. Basically, it's a trade-off of capacity and efficiency, which speed you choose. And so this is the terminology we're going to use, and it does get muddled up a bit. Sometimes they'll say, instead of full load, they'll say rated capacity. So hopefully that's not too confusing for people. There's also something I call normalizations that I'm going to be using a lot. There's a normalization called a ratio, which is the performance relative to a maximum compressor speed at a fixed temperature. And then there's maintenance, which is the performance relative to a less extreme outdoor temperature at a fixed speed. So maybe, I don't know if that makes sense just as written, so I'm going to go through quick examples to illustrate this. So this here is an example heating capacity data for a variable speed system found in manufacturer's product literature. It illustrates how the minimum and maximum capacities are changing across different outdoor temperatures. And if we wanted to know what the 47-degree ratio at minimum speed is, we would look up 47 degrees. We would find the minimum capacity at 47 degrees, which is 14 kBtu per hour, and then the maximum capacity at 47, which is 65 kBtu per hour. And then this ratio is just the ratio of those two. So the capacity ratio at minimum is 22% of maximum. And because this is normalized, it's relative. If we felt this was the representative of most units, then we could use this to fill in assumptions about what is the minimum capacity at 47 for other units as well. And that's why we use these normalized values. The next one is a maximum capacity maintenance, and the process is fairly similar. If we know the maximum, if we want to calculate it, we calculate the maximum capacity at 17 degrees, which is 39 kBtu per hour, and we calculate the maximum capacity at 47, which is the next less extreme temperature that we're looking at here. where we might have data. So the capacity maintenance here is 39 divided by 65, or 60%, which means that the equipment maintains 60% of its capacity at 17 degrees. So now our goal is to develop a map of performance for any operating condition that is also consistent with the AHRI certified data. So this chart here now I've replaced with a cloud of points, and these are, each one of these points represents the hour, the load at 1 hour of the year for a home. And as you would expect, the load increases at lower outdoor temperatures. But for a given piece of equipment, what we really need to know is at each one of these little points, what is the power and capacity, so that we know what the implications are for energy use of the heat pump system. The challenge is, as you may remember, that we only have 2 points for capacity. We have the 47 point and we have the 17 point. We also have the HSPF2, which is a weighted average of efficiencies at different temperatures and loads. And so right away, it's not really helpful to understanding what the power is at any of these points. And so with little to work with and historically little guidance, it shouldn't be surprising that there could be a wide range of interpretation of how to make a heat pump, how to model heat pumps and air conditioners, given the sheer number of points that we have to estimate performance at and the points that we're given. So to resolve this, Addendum 82 aims to flesh out a much more comprehensive performance map based on the best available data sources. So this means establishing performance at more temperatures. So maybe kind of a minimum temperature, a 5-degree point, which is often characterized, and then kind of an extreme point where maybe the equipment, is probably doesn't operate very often, but the compressor probably also has a maximum capacity there. And so there's a full range here. And let's see, and then we also need to establish performance points at the minimum capacity and the maximum capacity. And so this would give us enough to kind of fill in the rest of the map to figure out what is the performance at each one of these points. So points that are below the minimum capacity, this is going to be where your system has to cycle on and off to meet the load, and you're going to have some cycling degradation that's going to impact your energy use. Any point above the maximum capacity here, this is where you need to use supplemental heating to meet the load that the compressor cannot meet. Any point in between, this is where your system is going to be modulating or cycling between speeds to meet those loads, and you have to kind of interpolate between the data at the speeds that were given to get the actual performance at each of those points. So let's see. All right, so I'm going to illustrate how the addendum goes about setting up this entire performance map, but I'm going to start with a single speed system. So for a single stage system, we're going to say for heating, we're going to have try to find the performance at 5 temperatures, and for cooling, we're going to find 4 temperatures. That's going to be enough to cover the range of performance. So that's a total of 9 temperatures, and we have 2 metrics, so capacity and power, and 1 speed in this case. So we have a total of 18 values that we need to determine. We can start by filling in the information we already know from the AHRI directory. So the capacities at 17 and 47, capacity at 95, and then the EER, EER2 is actually just kind of the COP at 95, and we can then use that EER2 to calculate the power at 95. So we get that point. Other than that, we're maybe, a sixth of the way there to getting a full map. So the next step is kind of fleshing out these other points. And we do that for capacity here, for heating capacity. as soon as we have 2 points, we have enough information to make a straight line. And so we can extrapolate. Sorry, where's this? My computer seems to froze. There we go. We can extrapolate the values to other temperatures and for capacity. But for both cooling capacity and power, we only have 1 point. So we need another point in order if we're going to try to do the same thing and extrapolate out to those the full range. And again, we reference back to the Cutler curves because what they include here is these curves that are basically your capacity maintenance and EIR maintenance at different values of outdoor temperature. And so if we use those for cooling capacity, then we can calculate what the capacity is at 82 and then extrapolate out to the extremes. The next step then is cooling power at 82 right here. Fortunately, we don't have, we could use the values from the Cutler curves, but we also know that what the SEER value is. And fortunately, the SEER calculation is relatively straightforward. And for single stage systems, we can actually, with an assumption of what the cycling degradation factor is here, come up with a COP at 82 degrees. Now, the HRI standard has a set of equations for each, for both SEER2 and HSPF for each of the different types of staging equipment. So single stage, 2-stage, and variable stage systems. This is by far the simplest of the 6 of the combinations. So calculating SEER2 is for single stage is very simple, and we can use it almost directly to get the COP82. And with the power at 95, then we can calculate what the the power at 82 that we've already calculated, we can calculate what this 82 point is. And then we can extrapolate to fill in the rest of that, the cooling power values. For power, it's the only thing left for heating power here. For all the cases so far, we've had at least one kind of anchor point to start from. In this case, we don't. So what we can do, the Cutler curves will provide us an EIR maintenance, so we can tell if we do have the power at 47, we can calculate the power at 17, but we don't have that yet. So the question is then, what do we use for the power at 47? The last bit of information that we have that we haven't used yet is the HSPF2, which we can also calculate if we have the full performance map. So now this calculation, the calculation for HSPF2 is a lot more involved from the one that I just showed you for SEER2. So what we're going to do instead is we're going to resort to using good old-fashioned iterative solving. So we start with a guess value for what the COP at 47 is and use that to calculate the power. Once we have that, we use the EIR maintenance from Cutler to calculate 17. We extrapolate, and then we ask, okay, is our simulated or calculated HSPF2 the same as the value that we received from the HRI rating? And if it's not, then we start over. We put in another guess. So guess number 2 here. We do the same process. We check it, and you keep on going until eventually you get to a point where with more informed guesses based on previous guesses, you get to a point where it matches, and then we can move on. And what we've done now is we've established a full performance map that is consistent with all of the AHRI certified data that we have available to us. If you were to synthesize the AHRI testing procedures for this model and run the calculations, you would get the exact same HSPF2 and the exact same SEER2. Now, programming the whole AHRI calculations is actually asking quite a bit of the software developers, and just doing the iteration can take precious computer time to go through the whole process. So what we've done is we've pre-calculated the COP. The H1 here is the same as 47. So we've calculated what the COP is at 47 degrees at various combinations of HSPF2, and you'll see this is capacity at 17 divided by capacity at 47. These are both also values that we have available from the HRI directory. So if you have that information, you can then use this. We put all this data into a table in the addendum so that people can interpolate for whatever values that they actually have for HSPF2 or the capacities at 17 and 47. All right. So that completes the single stage systems. Now we move on to two-stage systems. For two stages, it's the same number of temperatures, same number of metrics, but now we have two stage. So now we're up to 36 values that we have to fill in. And I'm hopefully going to go through this a little bit faster because I think you kind of get the idea. It is also very hard to explain, and I'm trying the best with these graphics. I don't know if they're working for y'all, but if needed, I can kind of come back and go through them again. But we have the same HRI data, so we can put those in, those data in. We can use the Cutler curves again, and Cutler curves also have capacity ratios and EIR ratios for different speeds. And so we can fill in, again, all of the heating capacity information using the Cutler assumptions. And most of the cooling, again, we don't have the final piece of the cooling power, and we don't have the heating power. Unfortunately, the SEER2 calculation for two-stage systems becomes a lot more like the HSPF2 calculation for single-stage systems. It's a lot more sophisticated. And so what we're going to do here is we're going to do the same technique where we're doing an iterative solve to figure out what is the value. This time it's going to be the COP82 at minimum speed that would result in the same SEER as that we're calculating. And so we go through that process, we iterate, we find the values, and again, we provide a table. This is a graphical representation of it with data that allows the software developers just to look up what that COP at 82 minimum is, and given any value of SEER and the ratio of SEER to EER will impact the results here. And so this, the relationship here is remarkably linear, both in terms of different SEER values and different ratios. So we only really need 2 points here. And if you just do a linear interpolation and somewhere in between, it's very accurate. So we didn't want to overwhelm them with a bunch of data that wasn't necessary. Okay. And again, we do the same thing with HSPF2, where we can iterate to solve it, and using the Cutler maintenance and ratios, fill in the rest of the data once we fill in that value to solve that. Again, we get another set of tables here that we can use to do the lookup process for two-stage systems. All right, so that covers single stage and two stage. The next step is variable stage systems. Now we have 3 speeds, we have 54 values to fill in, and we can add the same known data from the HRI certified directory, but this time we can't rely on the Cutler curves to determine the maintenance and ratio values. This is because Cutler's work was done in the early 2010s, before a lot of these variable systems really hit the market. And so there wasn't enough data to really find something that we felt was representative at the time. Fortunately though, there's another resource that the Northeast Energy Efficiency Partnerships has assembled, which is a database of heat pump units that includes the performance beyond AHRI ratings. There are now almost 150,000 products in this list. Actually, this is maybe a couple of months old. I don't know what it's at now, but it is growing, and it's all built with voluntary data from manufacturers And the only criteria to be listed here is that you have to be part of what NEEP considers a cold climate heat pump, which means that it's a variable capacity or variable speed heat pump, and the COP at 5 degrees Fahrenheit for heating has to be greater than 1.75. And so this database obviously has a lot of data. And if you go to any one product, here's an example for a Daikin unit. You can see that it has the HRI data in it that we're looking for. And these dotted lines here represent optional HRI data, although I think almost always they provide the 17 degree point. So it's not, it's reliably available. It also includes temperatures be much further different from what what's available in the HRI directory. So we have a lower temperature that we can use as well. And this unit doesn't show it, but there are units that have a value at what's called the lowest catalog temperature, which might be much below 5 degrees and closer to where the compressor actually shuts off, where we need to know what that performance is, because the whole idea of cold climate heat pumps is that you're operating in climates where temperatures get much lower than 5 degrees. So this is all great. And obviously we can now supplement our traditional data with a lot more data at these different temperatures and different speeds. So we have minimum rated, maximum, where before we only ever had, well, rated / full. This is where that terminology can bite us. Full speed performance is the only thing that we'd get from the HRI directory. Okay, so as I said, this gives us a much more complete picture of performance. So we have all these additional points at a minimum, and we also often will have something below 5 degrees. And all of this data is now product-specific data, and the hope was that energy modelers could use this data directly to capture the more subtle technological distinctions among some of these heat pump products. You know, different heat pumps that use different strategies, maybe having lower capacity ratios or better capacity maintenance. You'd be able to capture that if you were to use this data directly. However, on closer inspection, some of the data is obviously problematic. Like in this example, we have a rated capacity that is higher than the maximum capacity, and you'd see the same thing where you'd have minimum capacities that were higher than maximum capacities. There's some cases where the COPs were greater than Carnot efficiency, which is physically impossible. And I think a lot of the data in here is not necessarily, you know, the manufacturers trying to make their equipment look better than it is. I think there's just a lot of data entry issues. And so we've worked with NEEP to build a much more comprehensive quality control checks. But it'll take some time to implement that and get the data corrected. And in the meantime, we decided that we couldn't really rely on individual NEEP records, but there's still a good amount of useful data that we could use to inform better modeling. So when we started this project, there were 125,000 listings, and of those, we found that 32,000 were inactive, so we didn't want to use those to help inform our modeling. And then of the remaining 93,000, 48,000 were duplicates. These are like the same unit, just with different branding, sold under a different brand by the same manufacturer. And then there were 39,000 cases that kind of violated those checks that we were looking at, like minimum capacities and Carnot efficiencies that didn't make sense. And then of the remaining 57,000 plausible units, there were some anomalous entries. We kind of looked like there seemed to be a data entry for all of the units for a given manufacturer. And then there were just some outliers, statistical outliers that we removed. At the end of the day, we ended up with about 3,500 usable units that we could use to inform a model, which is still a reasonable sample size. From this sample size, we were able to make histograms and look at the statistics of some of these values. So this is the rated capacity ratio, so rated capacity or full capacity divided by maximum capacity. You see again here, a lot of units use the same full capacity is the same as the maximum capacity, but a lot of units don't, and there's strategic reasons to do this. So for our model for variable speed units, we can use the average value here, which is shown in this line as the value that we use for our assumptions. The same thing, we have several of these kind of charts. This is the minimum capacity at 47 degrees. This would be the capacity ratio at 47 degrees. So meaning that the equipment can turn down all the way down to about 27% of its full maximum capacity to meet the load. And you can see the variation here. For our model, we're just going to use the average again. The same thing here. This is capacity and maintenance at 5 degrees. So we get all these ratios, all these maintenance values, and we can use that to flesh out a lot of the data in this chart. Once again, we have to find power values that match the CR2 and HSPF2 using the same iterative approach. We get new tables here for variable speed. So this would be CR2 values, and this is HSPF2 values to get the COP at 47. So that's it. So we fleshed out the entire performance map. Notice that we're not extrapolating here anymore. These are actual values informed by the data from the NEAP database, so that we can get better, more accurate, hopefully more accurate representations in those cold climates. And this really sums up a bulk of the work that went into this addendum. There are a few loose ends. I'm looking at the clock and realizing we only have about 20 minutes. Let me see how fast we can get through them, because I do want some time for questions and discussion as well. So one piece is the variability with indoor conditions. The COP here is this is actually heating COP. Will actually change depending on what the indoor temperature is and what the flow rate across the coil is. So this is something that manufacturers will provide in extended performance maps, but they're really hard to find. So we have to, it doesn't make sense to have to look up that information. And so we're going to use the Cutler curves, which include this variability to capture that in the simulations. For defrost is another big topic and another area where we have very little data available from the manufacturers about how the heat pumps work in defrost operation. And there's also a wide strategies that people can use to defrost the outdoor coil. And so, but with whatever strategies they're using, it's not always documented in a way that can be readily determined by a rater. So the assumptions about defrost, we decided that we're just going to use the same assumption across all heat pumps for every speed of operation, which is that it's a timed reverse cycle defrost. So the equipment is actually running in air conditioning mode so that heat is being rejected outside to melt the frost on the coil. And the assumption that we came up with is based on some studies done at the Central Valley Research Homes in California to establish a correlation where the capacity, you basically, because you're reversing, you're going into cooling mode, you have less capacity to heat. And so you have a degradation, you have 14% hit to your capacity. But also in the process of changing over, you're turning your compressor off. So there's actually, you also end up using 2% less power at kind of at extreme conditions. And it goes, starting from 0 at higher temperatures, ramping up to that maximum value. Now, we've also decided that defrost should actually only kick in at 40 degrees. This is something that might be unit specific or installation specific, but for the sake of this, we're going to impose this assumption. So really anything above 40 degrees, there would be no defrost. We also assume that the supplemental heater is active and the indoor fan is running when you're in defrost, and that there's a pan heater outside when the temperature is below 32 degrees. That uses energy to keep basically to if as the frost melts off, it doesn't refreeze and build up underneath the unit. Okay. The next one is the indoor fan power. As I mentioned, manufacturers provide the net capacity and net power, which lumps the indoor fan in with the coil. And so in order to get the gross performance, we need to make assumptions about the fan performance used in the AHRI rating process, so we know how much heat to remove from that from the net values provided. And we need to do that at every speed. So for AHRI ratings, the airflow ratio is relative to the full speed cooling operation. So a value of 1 here, this represents full speed cooling. For heating, full mode heating, you might have a different flow rate, and then obviously for different compressor speeds, you might have something. So if we were looking at capacity, let's see, if you're all of the flow rates are proportional to the rated capacities. So capacity ratio of 30% for cooling would mean that you're operating at this point, and depending on what fan motor type you have, you can then look up what fan power to assume for your rating. And then we kind of repeat the process using, instead of the AHRI rating points, we use the measured data from HVAC grading to establish a separate relationship based on the values measured. So these watts per CFM here, these are the assumptions that we have for the rating process, but those would be replaced with the values that are determined from HVAC grading. All right, I'm not going to talk about sensible cooling much, but just know that there's an approach to calculate the rated sensible heating ratio based on some algorithms developed by Proctor Engineering. And then we use something called the apparatus dew point methodology to calculate for any given entering conditions how much latent heat is removed from the airstream. The final one, second to last here, is operating performance. So like I said, anytime your equipment is below the minimum capacity, it's going to be cycling. For single stage or two stage units, we assume that there's a degradation factor of 0.08, which means that you're using 10%, roughly 10% more energy if you're basically cycling very often. And for a variable stage, we assume that it's closer to 70% with the C sub D of 0.4. Now these values are based on the single stage or two stage is based on a database that the California Energy Commission had on heat pump products, and the C sub D is based on a Purdue study. And my understanding is that variable speed equipment doesn't care as much about cycling losses because their minimum capacity is so low that you don't spend much time cycling. So it's not as much of a concern to get it for improved ratings. The last piece here is the crankcase power. We just assume that there's 10 watts per ton of rated full load net cooling capacity when the system is on, or sorry, when the system is not on, and the temperature is below 50 degrees Fahrenheit. Okay, so that gives a lot more information about how to model these systems for HERS ratings. As I mentioned, the addendum is out for public review now until the January 21st, so this is your chance to get public comments in. You can also reach out to me directly or RESNET staff if you have questions. A lot of work went into piecing this all together. I'd like to thank all the members of that working group. Also Nathan Oliver, who works with me at Big Ladder, who did most of that statistical analysis on the NEAP database. So that's all I have. Thank you.
Like thank you, Neil. We have a few questions. One is, and some of this you may have covered during your content, but I'm just going to put them out anyway. Why is the extreme for cooling 60 degrees and not something like 70? I can't imagine anyone running cooling when it's 60 degrees outside.
Yeah, well, there's actually a number of cases where you'd run maybe even lower. And that's actually something that we've discussed in the committee. If you have a very efficient home with a lot of solar glazing, then you might have a cooling load when it's relatively cold outside. And there's certainly cases that we've encountered already in simulations like that.
Okay. Sort of adding on to that, have you also tested these changes to see what kind of effect it has on the ERI?
We have not. It's a great question, because so this public review is intended mostly to get comments and just kind of the concept. It will most certainly not be the last public review, but with RESNET's new policy, before anything like this gets published and becomes mandatory or even voluntary, we will perform a HERS impact analysis to answer that question, so that people reviewing it once it is, at a further along in its process, will have that information alongside to better understand what the implications are.
Okay. Next, is there a level of confidence that the current ACA 310 verification process will still be able to capture all the value in heat pumps?
I think so. There's certainly complications for variable speed. I think all of the process, the ACA 310 process, is mostly based on single speed systems. So there's a question of how do we, on the modeling side, how do we translate that into for variable speed and 2-speed systems? Another piece of it is the fan blower, let's see, the airflow and blower watt draw parts of grading, because now that you have multiple modes and multiple speeds potentially operating, you need to know which speed and mode you're operating at when you do that draw, so that you can then kind of extrapolate out. There's certainly going to be complications, but I don't see the grading process as something that is not going to be reliable moving forward. I think we're going to be able to figure out ways to clarify some things as they arise.
I think you might have addressed this earlier, but were any heat pump manufacturers involved in sort of this working group, and is the list of the working group members available?
Yes. Let's see. I can make it available. I don't know if people want that publicly, but this is the group. So we had people from Lennox, Trane, and Daikin joining, and honestly, they were some of the least active members, but we did have did get a lot of early input in from a member from Daikin, and this really is. I know manufacturers have so many other priorities, right? They're changing out refrigerants, they're doing all these other things. So hopefully by doing this public review and by this webinar, hopefully it comes across some of their plates. I'd really like to get more comments from them.
Okay. There's a question, you might know this, if not, I can find out the answer from RESNET staff. Is there a need to submit a formal request for an extension of the public commenting period on this?
There's 11 days left. If that's not enough time, you can request it. It was admittedly out for public review across, over the holiday period. But I think that is ultimately a question for RESNET staff, what the process is. It's my experience participating in standards committees is most of the comments don't come in, and people don't start reviewing until like a week out. So there still is time, but if you feel like there isn't enough time, then I think you can reach out to RESNET staff. I believe Laurel can help answer that question.
We can find an answer for that. For the NEAP data determined to be physically impossible, does this consider the electronic controls of the equipment modes that may give results which are unexpected? And I can't read the rest of it. And sorry, hold on. And discontinuous, sorry, unexpected and discontinuous.
It does. I mean, there certainly are things that were initially unexpected, but we didn't rule those units out. Basically, we tried to make it fairly, like we we were realizing that we were removing a lot of units from these, and so we wanted to make it things that we felt very confident that this is physically impossible. Like I said, like a minimum capacity greater than the maximum capacity, or Carnot COPs greater than Carnot efficiency. There are certainly cases that are not intuitive, like where what the compressor speed will change at different temperatures to help improve capacity maintenance. And so I think what a lot of people think of as a compressor speed is it's the same RPM all the time, but like what they consider maximum speed might actually change the RPMs of the compressor to ramp it up and do more and increase capacity. And so we've accounted for that. There's a lot of things like that that initially were unintuitive, but we realized that that was realistic. And so we included that. And in fact, most of the units, most of the performance maps that come out of this process do exhibit that behavior.
Will this apply only to heat pumps? What about variable dual speed AC or even variable capacity furnace?
Can you repeat that, Valerie?
Right. Will this apply only to heat pumps? What about variable dual speed AC or even variable capacity furnaces?
Yeah, okay. Yeah, so this applies to both heat pumps and air conditioners. Variable speed furnaces is probably something that we would need to address in a later addendum, but furnaces are much, maybe this is a dangerous thing to say, but from my perspective, they're much simpler to model. Yeah, there's maybe some nuances there, but they don't have like a refrigeration system which has all of these challenges that impact the map of performance. When you think about furnaces, it's really just the speed that they're operating at. There's not a whole lot of other variables that impact, their efficiency and their performance.
Is there consideration for equipment that's not listed in the AHRI or NEAT directories, like air to water heat pumps?
Not in this addendum. That was one of the first things I went over, is that this addendum is limited to the scope of the same scope that's in the AHRI 210, 240, anything that's CR2 or HSPF2 rated. But for sure, we would like to expand, like improve the modeling methodology that's used, not just for RESNET, but other incentive programs code around the country as well. And that would incorporate best practices for modeling ground source heat pumps or package terminal heat pumps.
Okay, we got time for a couple more. If they do we know if this change will affect when a project uses the air handler for 62.2 whole home ventilation, or even if there is a OA pipe or not?
Yeah, this won't impact that. Where we draw the scope of this is the air entering into the blower fan, and so by that time it already includes some outdoor air. So if you're bringing in outdoor air and you're mixing it in with return air or whatever, you're going to have different lower entering temperatures than you'd expect, and the model should be able to handle that just fine, and is designed to do so.
Okay. You mentioned that this doesn't cover multi-split heat pumps. Will that be addressed in the future?
Again, ideally, multi-split heat pumps are another challenge because there's a lot of mix and matching that happens. I don't know. I think some might be rated with CR2 and HSPF2. If that's the case, then they would fit in. But if you're really trying to do something where you have multiple head units within one outdoor unit, I don't know if there is a modeling methodology out there that people really feel confident in, and so we certainly keep an eye on that.
Great. We're at the top of the hour, so I'm afraid we have run out of time for questions, but I believe you said you provided some of your contact information for folks to follow up. You can also send an email to our general inbox at info@resnet.us. I manage that box, so I'll be happy to share those questions with Neil. And as you mentioned, Neil, you will be presenting some of the same content at the conference later on this month, January 26th to the 30th. So I encourage anyone who's going to be attending to add this session to your calendar if you have further questions. Neil, we want to thank you so much for your time today and going over all that complex information. And for the rest of you on the line, thank you for staying with us, and we look forward to seeing you on the next webinar. These slides and the audio recording will be made available as soon as we can download the recording from the system. Thank you all so much. Have a great day. Thank you,
Thanks,
Neil.
Valerie.